All right, guys, let's go ahead and get started. Hope you all had a good weekend. Last week until spring break, I just now realized that. I don't know if you're looking forward to it as much as I am, but I am looking forward to it a lot. All right. Shh. It's great to see you all so excited about organic chemistry this morning. But let's take it down a notch so we can go ahead and get started. All right. So the other day, I introduced aromatic compounds to you a little bit. We talked about benzene. And so just to remind you, here's the structure of benzene. And I drew a resonance structure of this, where basically all the double bonds have kind of shifted around. Neat little history lesson. There was a guy that worked on, that investigated benzene and its discovery and its existence and its properties. His name was Augustus Kekulé. And so these structures are actually named after him. They're called Kekulé structures, in case you ever happen to run into the phrase or term out there. He actually initially thought these were two separate compounds that existed within equilibrium of each other. As we know now, that's not the case, right? They're not two separate compounds in equilibrium. They're actually the same compound in a resonance structure. So I think I showed you the resonance hybrid the other day. Resonance hybrid is just a hexagon with a circle in the middle. And I will use that quite a bit. I'll sort of go interchangeably between these guys. If I want to show a mechanism, I'll usually draw the electrons out. If I don't need to show a mechanism, a lot of times I'll just draw a circle. All right. One other interesting thing about these is that you'll note all of the carbons have exactly one H. Right, the formula for benzene is C6H6. We already said they don't get involved in addition reactions, right? You don't add to the double bond. However, one thing that you can do is you can do substitutions. Specifically, you can substitute a substituent, in place of one of the H's, right? So, you could stick in an alkyl group, right? So something like that. We've actually worked with this compound. This is toluene. And toluene, we've just substituted one of the H's with a methyl. You could substitute in a Cl. Sometimes you can substitute more than one of these. Say we did a Cl and an OH, right? So there's a process, or there's a name for this process. It's called electrophilic aromatic substitution. That's going to be the focus of our study next chapter, right? One thing that we want to go ahead and do right now, though, is we want to see how we can name these benzene derivatives. So we're going to do a little nomenclature. All right, so let's take a look. It's a little different than probably what you're used to. There's not a thing where we look for the longest carbon chain or anything here. Everything is named off of benzene as sort of a parent. All right. So first, let's look at monosubstituted benzenes. Benzenes that have one substituent hanging off. Now let's just say we have that. For most of these, it's very, very simple. what you do is say the substituent name, and then the word benzene. That's it. So what substituent do we have on this one? It's an ethyl, yeah. It's an ethyl. Then we add the word benzene, voila. Ethylbenzene. What would that one be called? Bromobenzene, yeah.
What happened to the double bond construction? Why are you writing this out now?
Remember, this is the resonance hybrid, right? So really, so when I did those two structures, I did these two resonance structures. Right? Really, the hybrid of these would be sort of like this. If we're doing the resonance hybrid, all 6 of those electrons are constantly spread out amongst all of those. So a really common notation for denoting this is the circle note. Okay. As you can see, nomenclature of monosubstituted benzenes is pretty simple. However, there are 3 exceptions. These are 3 species that, while you can treat them this way and it's technically correct, it's more accepted to name them through some common roots. So basically, you're going to sort of make a root name here that you're going to use for further nomenclature. All right, here's the first one. I've already told you this one. This is toluene. Now, you could also call this methylbenzene. And that's fine. That's not incorrect. But much more commonly, you'll hear this referred to as toluene. And more importantly, other derivatives of toluene will use toluene as sort of a base or root name. All right, so that's going to be, these 3 you're probably going to want to put to memory. All right, so you got toluene. You have an OH. You could call this hydroxybenzene, and that would be okay. But it's much more commonly known as phenol. You guys have probably encountered phenol, even if you don't know it. You guys done dissections before? That stink? There's probably a very good chance that phenol was used as one of the preserving agents. Formaldehyde historically has been used, but formaldehyde is really toxic, actually, so it's kind of fallen out of favor in recent years. So phenol has been one of the primary things that's been used in tissue preservation. Stinks to high heaven. I hate the smell of phenol. Once you smell it, you'll never forget. All right. And then you have this. You have a benzene ring with an NH2. You could call this aminobenzene. By the way, an NH2 group is called an amino group. But more well known as aniline. Where did they get all 3 of these names? I have no idea. But they're there, and we go on. Okay. Any questions so far? All right. All right, gets a little bit more layered with di-substituted benzene. Now, if you have a di-substituted benzene, that means you have two substituents, two H's, that have been subbed out for something else, right? Now, there's a couple of different ways that you can go about this. Yeah. You could have a situation where you have, I'll just use A and B here, just for generic representation. You could have something like that, where they're right next to each other. You could have something like this. Or you could have something like this. So you look at the respective positions of the substituents, like A and B. You know, over here, they're consecutive carbons. So we could say they're the 1 and the 2 positions. Here, they're 1 and 3. Here, they're 1 and 4. Right? However, we have other names that we use far more frequently. The 1-2 designation is often called the ortho positioning. That's abbreviated by a lowercase o. The 1-3 is called meta, little m. 1-4 is called para, lowercase p. Okay, so whenever you have a di-substituted benzene, you've got to indicate whether the two substituents are ortho, meta, or para to each other. All right, let's do a couple of examples. All right, so we have that. Okay, we're still going to use benzene as sort of our core root name here. Let's describe everything else though. It's got two substituents, right? What type of positioning do we have? We have meta, right? So you can write meta, or you can just write a lowercase m, either one's fine. Then we put in our substituents. What do we have? What type of substituents do we have? Well, what? Isopropyl and chloro. Guess how we write them? Alphabetical. Very good. So this is meta, chloro, isopropyl, benzene. All together, except for the dash between meta and chloro. I want to show you, let's see, put an I there. I'm going to show you a new substituent, one we're going to see quite frequently in the next chapter. NO2. An NO2 group is called a nitro group. Right? So what's the positioning here? Para. All right, so we have para. We have iodo and nitro, right? So we're going to write iodo first. Iodo, nitrobenzene. Okay. So far, so good. All right. Now, it's a little bit different again. when you start using one of the three special compounds? Whenever you use one of the ones that has a special substituent in it, right? This is a derivative of which one of those three special ones? Phenol, right? So in this case, our parent name is not going to be benzene. Our parent name is going to be phenol. What type of positioning do we have? Ortho, right? So we have ortho. Now, in the last couple of examples, what we did was we wrote the positioning describer, and then we wrote both substituents. In this case, one of our substituents is already represented in this name. So in this case, you only have to write the tert-butyl group. The OH is already represented in the parent name. So this is ortho tert-butyl phenol. Make sense? What's that one called?
Nitro, and
Metonitro what? Aniline. Yeah, very good. It's an aniline because it's got a benzene ring and an NH2. So we can use aniline as our parent. We have a nitro group as the other substituent. They're in a meta positioning, so. Okay. How about this one? This may be a bit of a thinker. Katie?
Would it be the
Paramethylphenol? Yeah. That works. This is a phenol, right? With the OH, so yeah. And it's got a methyl group in the pair position, so this is good. However, it's not the only thing you can do. You do occasionally run into something like this, where you can actually have two separate bases. So another possibility could be para. OH is hydroxy, by the way, in case you're not familiar with that. Para-hydroxytoluene. Now, which one's right? They're both right. Either one. So you couldn't go wrong doing this either way. Okay. That make sense? Any questions so far?
Would it matter, like on the left one, that you had the nitro group like in the top left position instead of the bottom?
If the nitro, instead of being here, was here,
Yeah.
it'd be the same exact compound. It's literally like, Matt, it's like you're literally grabbing this and just sort of flipping it over. Yeah, without any moving in groups. Yeah, it's exactly the same. Any other questions? All right, raise. Here's one. If you've seen this problem before, don't answer. You guys are giving me some weird looks out there. Any guesses? Paradox, doctor. Well, chemistry humor. I see people like, that is not real. Eraser. Messed up my notes now. Well, chemistry humor, paradox. You could, there's actually several of these. You could have done the same thing. Orthodox. So, paradigm. Yeah. I could do these all day. But there's one more I want to do. People have a hard time with this one sometimes. This is for all you biology majors out there. Oh, who got that? Yeah, this is metaphase. See, phases of the moon, metaphysicians. I would say show this to Annie, but I think she's seen it 1,000 times because I've always sent people say, hey, go show this to Annie. So, yeah. All right. Enough humor for today. Let's move on. Okay. So beyond di-substituted species, you can have polysubstituted. This is anything that's basically more than 2. So you could have 3, 4, 5, even 6 substituents on a benzene ring. All right. Now, we're not going to go through all the different possibilities here, but I'll just show you the general rules. Now, once you start getting polysubstituted species, you're going to have to start numbering the carbons in your benzene ring. So let's say we have something like this. All right. Do y'all remember how we numbered stuff on a cyclohexane ring or any alkane ring before? We treat it the same way, right? We're going to number to give the substituent, first of all, to give substituents the lowest possible numbers that they can have, assuming nothing takes priority. All right, nothing's going to take priority here. So where do you think we're going to start numbering? With the chloro, the bromo, or the ethyl? Yeah, I would agree. Chloro. If we do chloro and go clockwise, we can have 1, 2, and 4 substituents. All right. If we put those in alphabetical order, which we should, we have 2 bromo, 1 chloro, 4 ethyl benzene. Benzene's always going to be your parent name here. Please don't ever, well, actually, let me take that back. Benzene will be your parent name in this case. I forgot there will be a couple of exceptions. One thing I can say about all these polysubstituted examples, they never ever have ortho, meta, or para in them. I see people all the time trying to put ortho, meta, or para in a polysubstituted species. That only belongs with di-substituted. All right, so make sure not to use ortho, meta, para. Let's see. That's an interesting one. Now, what do you notice about this one as opposed to the last one?
You can number from each side.
What's that?
You can number from either side.
Oh, I wouldn't say that just yet. This one's got something else that's a little bit different from the last one.
Includes one of our exceptions.
It includes one of our exceptions. Always look for those, right? If you look over here, yeah, we have, this is a toluene derivative. So we want to name it as toluene, right? Now, whenever you have one of your root exceptions, by definition, the carbon with that substituent is carbon number 1. Doesn't matter what else gets what, that one gets carbon number 1. All right? So that means we're either going to go counterclockwise and have substituents at 1, 2, and 6, or we're going to go clockwise and have substituents at 1, 2, and 6. All right? Which one do you think it is? Are we going to go clockwise or counterclockwise? Which gets number 2? Cl or the isopropyl group? Y'all remember how we decide? When in doubt, use the alphabet. There we go. Yeah. Since we can have 1, 2, 6 on either direction, we're going to put the number 2. That's a more favorable, alphabetically favorable fluoro. So this becomes 2-chloro, 6 isopropyl toluene. Yep. All right. What can you tell me about this one? It's a phenol derivative. So that means this guy is going to be number 1. Now, in this case, which way do you think we're going to go? Clockwise or counterclockwise? We're going to go counterclockwise because going this way gives us substituents at lower numbers. Very good. So there, now all you got to do, you just got to put everything together, right? We have diethyl, so we're going to use E for ethyl as opposed to F for fluoro. So we're going to write that first. 3, 5, diethyl, 2, fluoro. Okay. That makes sense? Are there any other questions about nomenclature? Yeah.
Can we use the non-domain, or do we have to use the short exemption?
What's that?
Do we have to use the exemption shortcut naming, or can we use the normal?
You can use the other way. This is just the one that's used most often. Yeah.
For the bottom one, why is that one?
I'm sorry.
Like there's that one there.
Uh-huh.
That's even have primary carbon.
Oh no, it's not. It doesn't have anything to do with primary, secondary, tertiary. It means this is carbon number 1 in the nomenclature. So 2, 3, 4, 5, 6. Yeah, it's just for nomenclature purposes, not primary, secondary. Any other questions? All right. All right, well, let's shift gears a little bit. All right, the whole point of this chapter is to talk about aromatic compounds. And so we've seen a whole bunch of them here. We've seen benzene and a bunch of benzene derivatives, and they're all examples of aromatics, right? They're not the only ones. There are many, many other aromatic compounds out there that are not even benzene-based, right? So how do we recognize them? Let's take a look at the criteria. There's actually a set of criteria that a molecule must fulfill in order to be qualified as being aromatic. All right, here we go. All right, this compound must have a ring in it. Just a plain acyclic compound can never be aromatic. Gotta have a ring. Number two, that ring must be planar, completely planar. Now, you're going to have to go through and recognize these criteria when you're judging whether something's aromatic or not. This is one that you can't really always tell just from looking at a structure necessarily. So this is going to be one that, I tell you. So I'll say, classify these as aromatic or non-aromatic, assume all rings are planar, something like that. But that is one of the qualifications. All right, your ring must be completely conjugated. We're going to revisit conjugation. Number 4, you have to have what we call the Huckel number of pi electrons in your ring. What the heck does that mean? Well, there's a mathematical formula. 4n plus 2 equals the number of pi electrons. N has to be a whole number. All right. Make sure you got these down before I erase them. All right, can I erase? Nope, okay. Can I erase now? All right, let's take a look at benzene. Let's see how benzene qualifies. We know it already does because heck, we said it does. Did. All right, so obviously benzene has a ring. The whole thing is a ring. I can tell you it is a completely planar ring as well, flat as a sheet of paper. All right, so the biggest things that you have to look for are conjugation and the Huckel number. All right, so is this completely conjugated? Well, yeah, I think we talked about that already too. We said that all of these had an available p orbital. That's because of their hybridization. What's the hybridization of each one of these carbons in this ring? Yeah, they're all sp2. That means they all have an extra p orbital. And all of those p orbitals, like we drew the other day, can overlap with each other. So we have a completely conjugated ring system. All right. All right, now what we have to do is we have to check the Huckel number. All right, so let's write our formula. 4n plus 2 equals the number of pi electrons. So how many pi electrons do we have here in this structure? We have 6. So we would make this number 6. And what you do is you solve for n. For all you math majors out there, if I need to walk through the algebra, let me know. But I think we can probably safely say that n is going to be equal to 1 in this case. And that is a whole number. So that means our Huckel number of pi electrons is satisfied. And this one would classify as aromatic. Okay? Does that make sense? There's a 4-carbon ring. Why don't you look at that one for a minute and tell me what you think. Is this one aromatic? Yay or nay? What's that? Don't think so? Why not?
Because it's 0.5.
Yeah, it's only got 4 pi electrons, right? So you say 4n plus 2 equals 4. N would equal a fraction. It'd equal 0.5, 1/2. So this one is definitely not an aromatic compound. This one actually has its own special classification as well. We'll get back to it in just a minute, maybe in this class. We'll see. Like I said, there's lots of other aromatic compounds besides benzene, right? This one sort of looks like benzene, but it's actually a fused ring system. This is naphthalene. You know where you find naphthalene? Mothballs. Y'all know what mothballs are? Why would you? You're way too young for that. People used to frequently have silk clothing in their that they wore and keep them in their closets. And silk is a target of moths. So mothballs are a moth deterrent. So a lot of people will put these stinky mothballs in the pockets of, you know, their coats or shirts or whatever, so the moths will stay away. So there's your lesson from the past, your fashion lesson from the past. All right, but anyway, this is called naphthalene. Fused ring system, right? So looking at this, what you do is you incorporate both rings here together, right? And you follow the same rules. I can tell you that this is a completely planar ring system, right? So then you would have to make an assessment. Sorry, I see my mark here that didn't come out very well. There we go. Is this a completely conjugated system, ring system? We got 10 carbons, right? Do all of those 10 carbons in that double ring system have an available p orbital? I see some nodding. Yeah, they do, right? They're all sp2 hybridized. That means they all have one p orbital. Then you want to calculate the Huckel number. How many pi electrons do we have here in the system? We have 10, right? 4n plus 2 equals 10. 4n equals 8. N equals 2. So yeah, naphthalene absolutely is an aromatic compound. Okay. I'm not going to draw this because I'm terrible at it, but if you look in your book, you can also see there's a whole classification of aromatic compounds called annulenes. And actually, benzene belongs to this group. Benzene is an annuline. Basically, all an annuline is, it's a hydrocarbon ring that is aromatic, right? Benzene is a 6-carbon annuline ring. You can have bigger ones. And if you look in your book, I think they even mention some, like, you can have like 16 carbons, 20 carbons here and there. I cannot draw them for the life of me unless I have a picture in front of me, which I don't. But you can look them up on your own. All right. But they're basically just like bigger versions of benzene. So for example, you might have 18 pi electrons in a particular ring instead of 6. All right. We're not going to look at, really the benzene is the only annuline we're going to pay much attention to. So I'm not putting much of a focus on this, but I just want you to be aware of what they are. All right. Are there any questions so far? All right. So there's actually 3 different classifications we can make to a given compound. Number 1, it can be aromatic. Number 2, it can be non-aromatic. And we classify it as non-aromatic if one or more of the first 3 criteria is not met. At least one of the first 3 criteria is not met. All right. This is a completely conjugated triene. Is it aromatic? No. How can you tell? Not a ring, right? Yeah. There we got a ring. This one's not aromatic either. Why not? Not all the carbons are conjugated, right? This one up here is sp3, and so is this one. So that means there's not going to be an available p orbital there. So it's not completely conjugated. Right? Then you have the third criteria, or excuse me, the third classification. This one we haven't talked about yet. That is anti-aromatic. Right? Anti-aromatic is a little bit different. Anti-aromatic compounds fulfill your first 3 criteria for aromaticity. So anti-aromatics are also rings, they're also planar, they're also completely conjugated. However, their Hubble number is going to be different. Specifically, their Hubble formula. Instead of being 4n plus 2, it's going to be 4n. So if you all remember this one I had up there a few minutes ago, right? Cyclobutadiene. That's a ring. I can tell you it's completely planar. Completely conjugated? Yeah. However, we have 4 pi electrons, and we saw that did not work with the aromatic classification, but if we say 4n equals 4 for the anti-aromatic formula, n equals 1, we see that fits. So this is actually an example of an anti-aromatic compound right there. that make sense? Don't worry, we're going to see plenty of examples of these. Let's talk about stability. What did we say about aromatic compounds and their stability the other day? Very stable. They're very happy little molecules. What do you think is going to be the least stable of all three of these? Just intuitively. Nope. Antis. Antis have extra added instability. Anti, right? Anti means opposite. So, yeah. It's like any comic book fans in here? No? That's going to make my analogy really, really terrible. You guys have heard of Superman, right? You heard of Bizarro Superman? It's kind of like he's the opposite of Superman in every way. Kind of like that. The reason anti-aromatic compounds are so unstable is actually because of something we haven't talked about yet. It's because of something called molecular orbital theory, and it has to do with where their electron, what type of orbitals their electrons are placed in. Their electrons are placed in anti-bonding orbitals, which, again, we haven't really talked about, so I'm not concerned with that right now. Just remember that anti-aromatic compounds are the least stable of these three. Non-aromatics, they fulfill a wide range in the middle. All right. Okay. Maybe the fact I dropped the marker is a sign we should stop. In all seriousness, this is a good stopping place because the next thing I want to talk about is something called heterocycles, and that will take a little bit of time to talk about. So I'm going to save that for Wednesday. So quiz on Wednesday, it will cover Diels-Alder stuff. So Diels-Alder reaction and retro Diels-Alder reaction, as well as this chapter up through this point. Okay. Have a good day.